Hello class. I was going to go over homework 2 now. So homework 2 is where we switched into function properties. You see them listed here. This is everything you'll need to know. Domain and range. Boundedness. This should really say boundedness probably. Increasing and decreasing intervals is what that should say. Max and min should probably say extrema, meaning local maxes and global maxes, local mins and global mins. Left and right end behavior shouldn't be there at all. We said that actually we're going to save that for the next assessment, so don't worry about that. Then it says determine algebraically if the function is even, odd, or neither. I mean, we probably should add in, that you should also be able to explain geometrically why the function is even, odd, or neither. Okay, so whatever, let's do that. I think it would be nice to try to do as many properties as we can just from the function rule, not with a graph, just from the rule, to see how far we can get. And then when we're kind of stuck, when we have no idea what the properties would be without a graph to look at, then we'll talk about how to generate the graph. And once we generate the graph, we'll talk about the property. So that's my thinking. So what is this function? Well, as soon as you rewrite it as a third x minus 2/3, you realize it's just a linear function. And knowing that it's linear, you immediately know that its domain is all real numbers. Much more broadly, every polynomial function has a domain of all real numbers. And if you don't know what a polynomial function is, it's how do they do it? I don't know. Let's just say it's some coefficient sub n times x to the n plus some coefficient n minus 1 times x to the n minus 1 plus some coefficient n minus 2, I'm digging myself into a hole here, n minus 2 plus dot dot dot. It's just these expressions that have powers of x, starting at some value, going down by one, until finally you're just all the way down at, c2 of x squared, c1 of x, and finally some initial constant. But that's a polynomial. As long as the powers are integer values, as long as the coefficients are anything real, that's a polynomial. And it's always just that roller coaster shape where you've got these ups and downs and whatever. And in sketching that, you can see, of course, its domain is going to be all real numbers. How's it ever going to have a break? If you think about it, at least the way I like to think about domain, the only time you're ever going to have an exclusion from your domain is division by 0, right? And square roots of negatives. Those are the two biggies. And then there's a couple other specialties, of course. You hopefully remember that the log of something negative or 0. That would be bad. What other functions do we know have exclusions? I'm going to say that's it, honestly. At least that covers a huge chunk. So anyway, just to move on, after that big aside, we can see that our domain is all reals. Now, something worth saying over here is the range. It's going to always be all reals when the order of the function is odd. Because when the order is odd, remember, your end behaviors will be different, right? If you have an odd order, then you have an even number of turning points, which would mean if you're coming up from negative infinity and you turn 1, 2, 3, 4 times, you're going to end up continuing up, up, up. Let me not overthink this. When the degree is odd, your range is all real numbers. And a linear function is certainly odd, so it's all reals. So what do you do in the case of an even order? Then there would have to be some absolute max somewhere. You'd have to find that absolute max, and your range would be negative infinity up to whatever that absolute max is. Of course, the alternative is you could have you could have an even degree giving you a global minimum, and then your range would be that minimum up to infinity. How do you know if it opens up or opens down? The leading coefficient. Positive leading coefficients open up. So their ranges would be min to infinity. Negative leading coefficients open down. So their ranges would be negative infinity up to a max. Alright, again, I'm over explaining, but let's move on. Boundedness. We said there was 4 options. You're either bounded below, like this guy, or you're bounded above, like this guy, or you're not bounded at all, like this guy, or like a sinusoid. That's bounded, since it's bounded both above and below. Our linear function, of course, is just a line, so it is not bounded. Okay, again, with our line, we know that we have a positive slope, so we know that we are increasing. So our increasing interval would be over our entire domain, so negative infinity to infinity. Decreasing interval would be none. Now, max and min, we do want to distinguish between the global / absolute and local / relative. So global, none. Local, none. And it's like that for all of them. This is a very boring function in terms of extrema. Global min, none. Global max or local min, none. We said we're not doing end behavior. Determine algebraically if we're even, odd, or neither. Sure. So that's f of x. So we know that if f of negative x comes out to be the exact same thing, if it's still just 1/3 x plus 2/3, then we'll be even. If on the other hand we find that f of negative x comes out to be the opposite of 1/3 x plus 2/3, where that negative is factored out, basically, you want the exact opposite of the entire function. That will prove that we're odd. And if neither of those things happen, then you're neither. And that should be what's about to happen, is going to be neither. So what is f of negative x? It would be 1/3 of negative x plus 2/3. So that's negative 1/3 x plus 2/3, which is not equal to the original function f of x. And if you go to factor out that negative, we can clearly state that that is not equal to the opposite of f of x. Therefore, f of x is neither. Even nor odd. Oops. There you go. There's your algebraic proof. We should probably make a quick sketch now too, just because. So for a very quick sketch, plot the y-intercept and use the slope. Those are terrible, sorry. But our y-intercept is down here at negative 2/3. And then our slope is 1/3, so we rise 1, run 3. Rise 1. Am I bad at this? Run 3. So it's just a line. And then I'm just kind of saying you should probably be able to explain geometrically why we're even, odd, or neither. And again, if we try to reflect this over the y-axis, we can see that this half, sorry about that, we can see that, oh boy, okay, my tablet is not super good. Let me make that stop happening. Okay. Anyway, as I was trying to say, if you take the right-hand side and reflect it over, it's not going to coincide with the left-hand side. It's a clear miss. So we do not have symmetry over the y-axis, which means we are not even. That's your geometric argument. Now, for oddness, you can think of it a couple of ways. You could reflect and reflect. So fine, let's do that. If I reflect over the y-axis, I get this. Then if I reflect that over the x-axis, it just goes like this. And it kind of looks like I end up parallel to my left-hand side rather than coinciding it. So for sure we can say that no, we don't have the required symmetry about the origin to be odd, and that proves we're neither. All right. I will likely not do every question as in depth as I did this one, but I wanted to give you as much background on all the properties as I could. So moving on. This one, we already did this one, but that's okay. I would rewrite this. It's going to be negative x squared plus 4. I want to believe I told you guys that the order in which we transform is very important. And you are always going to want to do everything before you translate. Translating should always be the last transformation that you do. So let me get some axes going. And the terrible way I drew them last time makes me want to use my built-in tool. So there, looking good. So we know that there's only 2 transformations here. We would take our normal upwards opening parabola and reflect it downwards. Then we would shift 4 units up. 1, 2, 3, 4. So we can see there'll be a point there, point here, point here. 1, 2, 3, another point there and there. So I guess I lied. I said I was going to try to do all of the properties before we sketch a graph, but I lied. This is another polynomial, so like I said, it's got to be all reals. But this time it is even, so you know it'll have the same end behavior. It's got a negative leading coefficient, so you know it opens down. So we know that our range is going to be negative infinity up to some maximum value. And then the function's pretty simple. We can see pretty clearly that that maximum value is going to be 4. And our range will include it, so we use a squared bracket. Now, given that our range clearly has an upper bound, we're going to be bounded above, pretty obviously. And on the left-hand side, our graph is increasing, but on the right-hand side, our graph's decreasing. So we've got an increasing interval from negative infinity to 0. Then we decrease from 0 to infinity. Very important to remember that increasing, decreasing intervals are intervals of x values. X's only. Don't even breathe a word about the y values. Just doesn't matter. You're giving me the x's on which the increase or decrease occurs. Okay. For max, we've got an absolute max. Now you're giving me the y value, and it's going to be at y equals 4. Now that does mean that we also have a local max at y equals 4, because absolute extrema are always also listed as local extrema. For anyone who somehow missed this, if we had a higher order polynomial, something like this, then we could see this point here is the global max. It's literally greater than every other point on the function. But we also have a local max right here. And it's a local max literally because locally, if you built a neighborhood around it, you could build a small enough window where if you stay inside that window, then that point is a max. So that's a local max. And that's the reason why absolute maxes are always local maxes too, because by definition, as long as I can build a little window around this guy, and inside of that window it's the very greatest, well, of course I can. It's literally the absolute greatest. It's the greatest even if my window was the entire function. So that's why you have to count it both. For mins, we're going to go none and none. There's literally no absolute min and no local min. We're not doing these. And then let's prove if this thing's even or odd. Because we sketched, we already know. We already know what we're going to be. So that makes the math even easier. I'm going to take the function in its original form, because I'm supposed to. And so basically I got to prove that the function f of negative x just comes out to be the exact same thing. So we get 4 minus negative x squared. And from here, if you just kind of went, okay, so that's 4 minus x squared, because the negative cancels out. That's a little too hand-wavy for my taste. You're really not explaining why that happened. So if we're in the middle of an assessment and you're trying to actually earn points by demonstrating knowledge, I would do this. I would break down negative x to the product of a negative 1 and an x. Suddenly now both of those are getting squared, so you apply the squared to both of those. And now we've got a firmer justification. We've got negative 1 squared. That's clearly positive 1. Getting multiplied by an x squared. And then that simplifies plainly with plenty of sort of steps shown indicating that you really know what's going on. By the way, guess what that function is? It's the original function f of x. So now, again, if you're really trying to blow me away with what you know, then you might want to say since f of x equals f of negative x, f of x is even. And of course the geometric definition is, well, we've got reflectional symmetry over the y-axis. That's even. That's it. Next. Oh yeah, the radical one. So I didn't like this one because you basically have no idea what this looks like. And you just never will. So if you don't know what this looks like, and you're not allowed to go to Desmos, then you build yourself a table of values. And starting at 0, we get root 4, which is 2. If you go out to 1, then you get root 3, which I don't care for. You go to 2, yeah, at 2 you're going to get 4 minus 4, which is 0. Negative 2, you get the same thing. So we kind of ran through this idea in class. I think we plotted these 3 points and we figured out our shape that way. So we know for sure that the point 0, 2 is on here, and then 2 zeros on here, negative 2 zeros on here. And then plotting the other points, I guess, would give me a bit of an idea. I'm pretty sure, I think I said to somebody that the graph looked like this or something, more like a bell. And that's because I confused it with a different function. It's not like that at all. And so plotting a couple more points would kind of indicate that we are really high at first, but then we kind of decay quickly. It's exactly half of a ball. It's a semicircle. So we should know that. Then the domain becomes easy. We can run from negative 2 to 2. Anything bigger than 2, though, when you square it, will be bigger than 4. And 4 take away something bigger than 4 is going to be negative. And the square root of a negative is non-real. So those values can't be in our domain. We can see that our range is going to run from 0 to 2. We are bounded, both above and below. So you just write bounded. Our increasing interval is on our left-hand side. So negative 2 to 0. And we're decreasing on the right-hand side, so 0 to 2. We have an absolute max at y equals 2. So which means we also have a local. But that's it. These endpoints are going to be absolute mins and local mins for us. Not doing this. We again can see that our symmetry is going to be even, but we do have to prove it algebraically. So what is it? 4 minus x squared? Basically, it's going to run exactly the same way, right? We're going to say f of x equals 4 minus x squared. And basically, we have to show that f of the opposite of x turns into the same thing. So you plug in the negative. It's under a radical. The radical just doesn't even matter though, because as we showed before, the negative x squared is going to become plain old x squared. So we do land right back at the original function f of x. Forgive me for being lazy here. I'm not showing the whole factoring out the -1 and the x and distributing the powers to show why the -1 goes away. I'm not going to do it all again because we already did it. We did it in the last one. When you guys take the assessment, you should. If you're actually getting graded, you should show that. I'm just not doing it. And then you should write me a sentence too, something grammatically correct, but not terribly long. You'll just tell me, therefore, you can use the 3 dots if you want. F of x is even. Here's 4. I always have trouble with 4. I would flip these terms around. Yeah. Now my problem with this problem, every year I forget about this, is you really have to factor out that negative, and then you've got this x minus 2. And I don't think you guys talked about this a ton, but when you study transformations, you put an a value out front, you put an h value on the inside and a k value on the outside. What you didn't do for some reason is put a c value on the inside that was multiplying the inner expression. That c value is what we have here, and that c value always has to be factored out. It has to be factored out. Otherwise you'll make the wrong decision. I mean, imagine something as simple as 2x plus 10. If I asked you how is this function translated, you'd be tempted to say that it got translated 10 units to the left, right? You'd be wrong if you said that, especially if there was a negative on the front. You have to factor that out, -2. Then you can answer questions about the translation with your new number, which would be -5. So we don't actually translate 10 units at all. Not when there's a 2 here. You got to factor that 2 out. We're translating 5 units. If that 2 is negative, then when you factor it out, it'll change the sign. So we're not going left, we're going right. So it's super important that that c value gets factored out before you make any decisions about your translations. So with all that said, I'm going to switch the order and factor out, and now I can see that my graph, should I choose to draw one, is going to be my classic radical function shape. It would start at the origin and go up to the right, but I can see that I need to be reflected over the x-axis. That's the effect of the c value, reflects over the x-axis. So now I'm a little square root function that goes that way. But then the -2 wants to kick me to the right too as well. So our little vertex is actually sitting here, and we open that away. So given that picture, we can now answer all these domain and range questions pretty easily. We can see that our domain goes from -infinity to +2, including the +2. We can see that our range is 0 to infinity. We're bounded below. The function is never increasing. It is decreasing on the interval from -infinity to 2. It does have a min. Its global min, aka absolute min, is y equals 0. Which of course means it has a local min at y equals 0 as well. But there's no other points of interest. For maxes, we'll say none. Forget about end behavior. Prove whether we're even or odd. From my sketch here, you can see we're neither even nor odd. But let's make sure we see how that justification looks. So what is it? 2 minus x? That's f of x. So you find f of -x. And it's 2 minus -x, aka 2 plus x. which I'm going to go ahead and go out on a limb on and say that's not the exact same as square root of 2 minus x. Therefore, not even. And if we do the same thing to try to prove whether or not we're odd, then we get to where? The 2 plus x thing all over again. You just can't even force this. It's just clearly not what we want. But no, I don't even know how you'd get a negative in front of it. So maybe at this point you would just say that's not equal to the opposite of the square root of 2 plus x, 2 minus x. Here we're trying to be 2 minus x. I don't think it's a stretch to just say, hey, this thing is not the same as this thing. They're clearly different. Therefore, not odd. So, f of x is neither. Just make sure, if you're going to say that the function is even, all you got to do is prove it even. If you're going to say it's odd, all you got to do is prove that it's odd. If you want to say it's neither, that's more work, because you have to prove to me that it isn't even and that it isn't odd. So there. Alright, that was 4. 5 is just x cubed. I talked about it as being a polynomial function. It's got odd degree. Domain is automatically all reals. Range is automatically all reals. If you didn't already know, the graph of x cubed just goes like this. That's not very symmetrical, but you get my gist. So domain and range would both be all reals for sure. Boundedness would be not bounded. The function is increasing over its entire domain. So the increasing interval would be negative infinity to infinity. None, none, none. Save it for later. It's obviously odd. But why? Why is it odd? Well, you do the math. You find yourself f of negative x. It's negative x cubed. And then this one goes down a little differently. We get the negative 1 x. It's all cubed. This time we're raising to the power of 3. So negative 1 cubed doesn't just turn into a positive 1. It's still going to be a negative 1 times our x cubed, which gives us negative x cubed, which is exactly what we wanted if we were trying to prove that we were odd. So we've just shown it that okay, spaced out for a second, writing all that down, but we'll say since f of negative x equals negative f of x, the function is odd. And we've got the work up here to prove it. I think there's one more. Alright, it's another polynomial, so I can instantly say in my domain that it's all reals. It's a polynomial of degree 3. I can instantly say for my range it's all reals. Since the degree is odd, I also know I'm not bounded, because one branch goes up and up and up forever, the other branch goes down, down, down forever. Now the increasing, decreasing part, I don't know. We're going to have to sketch this now. We can factor out an x. We can factor and then we can do our best to sketch the graph by plopping those values down on the grid and trying to see our shape. So one of our zeros literally is 0, because that's the 0 of this factor. That gives us a x-intercept of x equals 0. Plot it. Then this guy gives us an x-intercept at x equals positive 3. And lastly, the last one gives us negative 2. So you can plot a point there. Then what do we know? We know that because we're odd with a positive leading coefficient, our right end behavior goes up. We know that we're odd, so our end behaviors have to be different, so our left end behavior goes down. And then you just know there's a couple of hills here. This must continue up and come down. This must continue down and come up. But it would be a good idea probably to find a couple of points just so we know how high these little hills are. Are they shallow little hills or are they kind of tall? We can't tell. So let's do the math. Make a little t-chart. We probably want to know what's happening at -1. So evaluating at -1 is giving me -1 cubed, which is -1, minus -1 squared, which is 1, minus 6 times -1, so plus an extra 6, I'm getting 4. So that's actually pretty high. We got to come up, hit that point, then come back down. We should also evaluate at +1. At +1, we get 1 minus 1 minus 6. So -6. Oops, I missed that point. You really should be careful to hit your points, so I'm going to do this again just as good modeling. That should go up, up, up. That's it for number 6. So what do we just figure out? We figured out that we increase, well, we don't even honestly know because we don't know the coordinates of this point. Just to play a game, let's pretend this is the point A, comma B. Let's pretend this point is the point C, comma D. And everything else is known to us. So then our increasing intervals would be -infinity to whatever the heck A is. And then also from C to infinity. And you can do the same with decreasing intervals. We see we decrease between A and C. And that's it. So what about the maxes and mins? You'd have to say local max is at y equals b, whatever that local max is right there. We never figured it out. So we're going to call it b. We've got a local min as well. And it's at d. Alright, looking good. None of this. Our graph is pretty clearly not even or odd, so I don't feel like doing it. I'll do the algebra. Cubed squared 6x. Is that right? Nope, all minuses. Okay, if that's f of x, then you're going to find f of -x, which is going to give you -x cubed, -x all squared, and 6 times -x. So what happens? This term stays negative. That kind of makes me think, what? Kind of makes me think we're going to be odd. But then the next one kicks in. This negative just cancels. Now that feels like we're going to be even, which makes me think we're probably neither, which of course we are. It's going to be neither. That turns to a +6. So what is this expression right here? Well, it ain't f of x. And if you factor out the negative, you're left with x cubed plus x squared minus 6. And that's not even, that's not odd. Yeah, that's what I'm meaning to say. So we're showing f of -x is not the same as f of x, therefore not even. We're saying f of -x is not equal to negative f of x, therefore not odd. So f of x is neither. Hopefully we're done. Maybe there's one more. Oh, we're done. Good. Because I'm very tired. I apologize for yawning through this and going catatonic at points. Anyway, hope this was helpful. See you later.